Okay. Hey everyone, how's it going? Hope everyone's having a great Monday. My name is Brad Miro. I'm a senior developer advocate at Google Cloud based here in New York City. And today I will be talking about how to power up your Apache Spark runtimes using native acceleration. So some of the things that we're going to go over today include JVM bottlenecks, calm their native shift, and then go into some of these specific some of these native execution engines specifically, including Gluten, Velux, Rapids, and Comet. And then we'll go over a couple of examples of where these are being used today. Okay, so you've just spent the last hour, learning about all sorts of cool Spark stuff, and this is how to actually make all of that stuff run faster. But what are some of the bottlenecks? Like, why do we even care about this to begin with? What does this actually mean? So when we talk about native executions, as Spark works today, you write your Spark code in either Python, Java, Scala, R, or SQL. That then gets converted using the Catalyst optimizer into a physical plan that then runs in the JVM for the most part. That's clearly a very high level abstraction. But what that means is that you're essentially limited by the capabilities of the JVM, for better or worse. So what we're going to talk about here is like why you would potentially want to move away from the JVM and use some of these other engines to actually process the Spark code. And some of the reasons for that is that the JVM focuses on a row-based volcano model. What that means is that data is processed one row at a time, and that actually produces a lot of high overhead inside of the JVM. There's also the pressure of garbage collection, where as the Spark code is processing, it's creating many short-lived Java objects during heavy aggregations that can trigger frequent garbage collection, and of course the infamous OOMs that we've all dealt with as we're debugging our Spark code. And then there's also a mismatch with modern hardware. Traditional JVM just-in-time compilers can't necessarily reliably auto-vectorize execution loops. So the high-level takeaway here is that the JVM doesn't necessarily natively do columnar processing, as I'm sure you're all familiar with Parquet. That tends to just be a more efficient way to do it, especially as you're dealing with large-scale data. The JVM is not optimized to do that. So what can we do about it? Well, we can move the columnar. So I call this the columnar native shift. So what this means is that we want to take the Spark code that is being run on the JVM and convert it or have it run in a different runtime that is better suited to columnar data processing. So the way that this works is that Spark still remains the orchestrator. So your code actually does not change at all. We're going to talk about that in a second. But Spark remains the orchestrator using Catalyst to optimize and generate the initial query plan. But then when it comes time to actually processing the code, we swap the JVM for native libraries. And the three that we're going to talk about today are C++, Rust, or CUDA. Compute-intensive operators are processed in columnar batches using Apache Arrow, and then returned to the Spark client with the same output that you were otherwise expecting. And again, the idea here is that zero code changes there's a little bit of an asterisk here, but the general idea is that nothing inside of the Spark code itself actually changes. This all happens entirely at the configuration level. This supports all of the Spark languages. So again, it doesn't matter if you're using Python, Java, Scala, R, SQL. The idea is that the code that that your Spark job is written in is decoupled from the actual execution. There's also deep support in several of these. It's still growing for open table formats. So for instance, if your data is in Apache Iceberg, many of these runtime engines have also integrated support for reading the metadata out of Iceberg and more efficiently processing that. And in terms of the actual speedups, there is a bit of a range. From what I've seen is that in general, for sufficiently large data sets, it'll be at least double. There's some evidence, some of these can go up to 7x. Actually, Rapids claims that for machine learning training, they've seen speedups as much as 100 times. I have not seen that myself personally, but we can buy that. But in general, you're looking at like a 2 to 3 to 4x speed up again. And generally speaking, the larger data set that you're working with, um, the larger the speed up will be. You really start to see these as you're working in the hundreds of gigabytes or terabytes or petabyte scale is really where you're going to start to see some of the speed ups. Okay, so let's start to talk about some of the tools that are actually in this ecosystem, and we'll start with Apache Gluten. So Apache Gluten, it is an Apache project, but I just add for some of these, I just added the companies that they originated out of. So Apache Gluten was started over at Intel. Maybe y'all have heard of them before. So the idea here is with Apache Gluten, you have the when you're using Gluten. So when you're using Spark, the query plan gets generated. And then before the actual processing occurs, Gluten intercepts the plan and translates it into a serialized plan. Now, what's interesting here is that Gluten itself is sort of the middleware between the Spark code itself and the native execution engine. So Gluten supports two different ones. This will make sense once I talk about the next slide, but essentially Gluten will take the Spark code and determine where in the Spark code we can take that and push it to a native execution engine. So in this case, it'll be either Velix or I believe they also work with ClickHouse. So the way that this will work is that, again, Gluten intercepts the plan. It knows which jobs can be pushed to the execution engine and which ones maybe can't. And then it'll also it'll handle the returning of the data also. So essentially, as the code goes, as the data goes between the JVM and the runtime engine, and then back to the user, it handles all of that. And then in this case, Gluten will work with a C++ engine called Velix, which we'll talk a little bit more in just a second. Now, here's the thing though, this is not foolproof. Not every single operator can necessarily be converted down to C++. So we need to account for that. Things like, certain Spark SQL expressions just aren't supported yet. Custom UDFs, of course, can always be a headache, and there's a lot of variance in what you might see in there. Some complex storage connectors are not necessarily supported. So like I mentioned, there's some support for Iceberg, but there might be some others, or like new ones, for instance, that just don't have rich support yet. So again, Gluten will expect every operator, and it will know which ones it can push down and which ones it can't. For the unsupported ones, it'll just use the JVM. So what is also really nice is that there is a hybrid approach where certain operators can still run on the JVM, some can still run on the native execution engine, and there can be that back and forth. And then the theme of, I feel like, everything with performant big data workloads these days is using Arrow. So of course Apache Arrow is used here as well. So that's that's supported right out of the box, and that's what is going to assist with some of that data conversion as well. Okay, so next we talked about Gluten. Let's talk about Velix. Now these two are. Oh, that was weird. So these two are often, they're paired together. They work really well together. This is generally where you see, when there's one, there's the other, generally speaking. So Velix itself is the actual execution engine that Gluten is pushing the code down to. So the way it works is that it supports vectorized execution. Operations are performed on dense columnar C++ arrays, which help maximize CPU cache locality. Oh, I guess I'll also call out. So Velix is not currently an Apache product. It is a project. Excuse me. It is open source, but it is currently being primarily maintained by Meta. Hence the Meta in parentheses here. So we talked about the vectored execution. We also have adaptive optimization, where Velix will dynamically adjust strategies based on real-time statistics during query execution, which I think is pretty sweet. It does support complex nested types. So as we're seeing more arrays, maps, and structs inside of data sets, Velix can support this. And then it also has advanced memory management, including off-heap allocation with integrated disk billing. And that helps reduce and gracefully handle OOMs. And it uses something called Velix Promise. Okay, next we'll talk about NVIDIA Rapids. So as you might guess, this one uses GPUs. So NVIDIA Rapids is a project that deals with GPU accelerated analytics. It maps compute-heavy operators directly to your NVIDIA GPUs via a CUDA-based engine. This is all built into a library called QDF. This is what will supplant the Spark JVM execution by mapping columnar data operations to GPUs. As you can imagine, GPUs are very well suited for columnar data processing. So this is a great thing to be able to take advantage of. In addition to QDF, we also Rapids also has QML, which vectorizes classical ML-based workloads like k-means and logistic regression, such and such. So you can kind of think of it as like QDF. It can work with some of the Spark data frame workloads, and then QML is sort of like the Spark ML drop-in replacement, if you will. What's kind of neat about this, I found, is that you can actually get a lot of out of, let's say, like a single GPU, just because of how efficiently these things run. So like I've seen clusters that are just like a main, like a primary worker and then a single GPU. They can't do a ton, but it can do a lot more than you think it could. And now, in order to identify what some of these great use cases are, there's an offline static qualification tool that can assist with identifying workloads that can benefit this by analyzing historical Spark logs. Because again, it's not going to be everything. If your workloads are very heavily custom UDF based, then you might not be able to get as much out of this. But if you're dealing with a lot of, let's say, traditional operators, like group bys, joins, selects, filters, like a lot of the basic stuff, then you can get a lot out of these execution engines. Another feature that Rapids takes advantage of is the NVIDIA UCX Shuffle. So this is an accelerated shuffle manager powered by Unified Communications X, which reduces I/O dependencies, and that it also enables GPU to GPU data transfers across the network, which helps avoid costly GPU transfers. So you can also build a network of GPUs and be able to take advantage of them, in one cluster. Okay, so next up, we'll talk about another project that's called Apache Data Fusion Comet. This is, again, an Apache project, but it comes out of and is primarily maintained by Apple. So this is one of the newer ones on the list here. It is it's relatively new. It's built on top of Rust, which I feel like we're continuing to see more and more of these days. It's an awesome project. I definitely recommend checking it out. One of the main benefits of this is that Rust can, again, this is big asterisk, but generally speaking, Rust can match the C++ performance while eliminating many of the pitfalls that C++ provides. And this, primarily comes from compilation enforced safety, which is pretty sweet. This has its own fallback mechanism when Spark operators cannot be run natively. They all sort of do. It's just, this one is baked into the project itself. And then also, like Velix, Data Fusion Comet runs on CPUs and is also Apache Arrow based. In this instance, Data Fusion itself is the runtime execution engine. That is, it is framework agnostic, and then Comet is a tool that essentially is the plugin for using Spark. But Data Fusion does more than just accelerate Spark workloads. Okay, so then just a couple of high-level examples here, just some areas where I've seen this stuff happening. So Palantir Foundry, they deploy Gluten and Velix across some heavy data pipelines, which they claim is dramatically reducing their compute hours and failed jobs due to out-of-memory errors. Apple's driving the development and deployment of Comet, as we mentioned, but they're using it internally to optimize some of their analytical workloads, and this way they can do it safely. And then Capital One is using Rapids on AWS EMR. EMR is their hosted Apache Spark clusters to process massive credit and fraud risk pipelines, accelerating runtime from hours to minutes. And then, okay, so another one that I didn't mention, I was going to show this here. So I mentioned I work at Google. We also have our hosted offering is called Lightning Engine, which is essentially taking our managed Spark offering and applying Gluten and Velix on top of it. So what I did was I ran a couple jobs earlier, and I can't show it here, I don't believe, but I ran 2 jobs. They each were just processing a gigabyte of data, and Lightning Engine did speed it up by about 1.5x. And I can show you here, these are just 2 images I snapped in the Spark UI, quite literally 10 minutes or 20 minutes ago, where this is the UI without using Lightning Engine. So this is just using standard JVM, Spark. And then here, this was using Lightning Engine, which had Velix and Gluten in there, and you can see that the individual steps change. So we have the the Velix Spark plan here. We're doing a collect, a shuffle, collect. So it will literally show you in the query plan where these things are changing. So it's actually pretty cool to see. It's also helpful to see, okay, what operators maybe weren't able to move over or not, just based on the nature of your job. Yeah, and then so here's the links to all these projects. If you want to get hands-on with some of this stuff, I actually wrote a code lab using Lightning Engine on Google Cloud, and you can quite literally do the benchmark on a 1 gigabyte data set or more. There's the option for more to just see what the performance increases look like, and you can dive into the Spark UI. It was honestly very insightful for me to learn more about this stuff as I was building that. But yeah, you can go to the top link there for that. And then here I just have the home pages for all of the other projects. Really interesting stuff. There's honestly so much more to this that I'm still learning about, and I'm sure some of you in this room probably know more about some of these projects than I do. But yeah, it's really cool. I think it's just nice to see that as we're all Spark developers here. Spark is an amazing tool. It's super popular, but it has its own limitations. And as we're looking for ways to optimize it, you can of course use amazing tools like DataFlint to help your tool run more efficiently. But there's also other ways that you can optimize it by looking into utilizing lower level engine support. So it's it's a cool time to be in the field. So yeah, that's all I got. Thank you.
Questions?
I deploy like Apache Runtimes, then just change the configuration to bridge this Runtime to the Velux library, or how does it function? Like, do I need any changes?
Yeah, so you just have to install the libraries, and then there's certain Spark config that you set before you kick off the job. No, they're just libraries. Yeah, it's essentially you're adding a library that tells like as Spark is processing, it just intercepts it and then can redirect it. So yeah.
More questions? I will add that it's like very platform dependent. So like with Google, you can with one checkbox enable the Lightning Engine, which is gluten based. In Databricks, you can with one checkbox enable Photon. Rapids require installation of drivers because it's GPU based. Gluten could be hard to it's a jar, but from a person in the gluten team previously, it's it could be hard to compile and make it work. Data Fusion Comet is really just a jar and it's working out of the box. Might not on all CPUs, but but it's the newest project, so it has the least support or deep features like nested columns and stuff. So it's very depends on the platform.
With all these different tools, can you mix and match them, or is it or they take one takes the space of another?
Ooh, that's a good question. I have not tried that. I would guess that they probably don't mix and match very well because they're kind of. I don't think there's anything let's say, if you have gluten and Velix and you had Rapids. To my knowledge, and if anyone else knows this, please jump in. I don't think there's any tool that can figure out if it's better to accelerate in C++ and Velix versus CUDA and Rapids. But that's an interesting thought. I don't know if anyone else has seen otherwise. I don't know if many of you have.
Yeah, a small tip, always look at the Spark UI or DataFlint UI, because even in the open source, we support all these libraries and know to format them well. So like the first tip is just to see if you have a fallback. Let's say you're reading CSV. CSVs are not supported in any of those platforms, so you don't see any performance boost. So if you pay for Photon 2.7x regular cost, or buy a very expensive GPU just to find out that it's not doing anything because it's reading a CSV, or it's doing a complex join, or like all your code is actually a Python UDF that is not vectorized. So first, just check that your code can actually be vectorized. So that's my biggest tip here.
Piggybacking off this question, these are, you said these are libraries. So like if I'm working on like a board-wide Spark cluster, I can still decide to use like one of these tools. You know, you have to a company level.
I mean, you'd still have to deploy it into the runtimes themselves because it's, you know, the execution is still happening on the worker nodes, and they need access to those libraries to know, oh, should I be using the JVM? Should I be using C++? So yeah, it does have to be deployed across the whole cluster. Mm-hmm. Yeah, definitely. Mm-hmm.
I noticed in Velox, and actually with JVMs, you're going to run into OOMs or OOMs. Do you see Velox as a way to mitigate the OOM, possibilities? And the other thing with, I'm an old C++ hack, there's always a issue with memory pointers or pointers that are not pointing. So does Velox help mitigate this, or what can we expect with something like this?
Yeah, so my understanding of the question is yes. So Velox is designed to. I don't believe that it is entirely intolerant, but it is designed in such a way that a lot of the reasons that the JVM might Velox just simply won't, because of just the way that C++ operates. It's number one. Number two, I'm sorry, repeat your second question.
Since C++ is pointer
Mm-hmm.
that's the other gotcha, so to speak.
Yeah.
Look at pure C++ code, but a Velox can, as I said, maybe mitigate some of that. One less thing that the developer has to loop through and work with. I'm not saying it's bad product.
No, sure. So what's really nice about all these is that you don't, whether you're using Velox, C++, Rapids, CUDA, Data Fusion, Rust, as the user of the tools, you don't actually have to utilize the engine underneath. So like as you're using Velox in your Spark cluster, you are not writing any C++ code. So that should be taken care of for you. It could always happen like any tool, but I personally haven't experienced that as I've used it, but yep.
One can always write a POC, test it on a dev environment.
Yeah. Yeah. I mean, like anything. Yeah, I'd say like anything, you definitely want to, especially if you're going to roll this out in production, you definitely want to test it and make sure. And, like nothing's ever immune to bugs, of course. But, generally speaking, as you're running these, they'll help you, like as you integrate it and test it, they'll help you perform faster. I know a great tool to help you debug them as well. So does DataFlint support all three of these?
Yes, and more.
All right. There you go. Question, Tom?
Yeah. So you touched on the strengths of these custom queries. Generally, what are the rules for which ones that sell at certain complex queries, which ones that sell at which
Generally speaking, and I'm actually curious your thoughts on this. Yeah.
Rapids and Gluten has great support for nested types. Iceberg is like iffy on both of them. Data Fusion and Comment has like the least support because it's the newest, but it's also like the easiest to install.
There are going to be things like UDFs that just none of them are going to be particularly good at, just because of the variance of what can be in those.
But one cool thing, UDF, like there is a new type of UDF, and you write it on Rapids, it's actually converted to CUDA. So you could write like your own UDF, it's actually being like run on GPUs. The cool use case. Last question? Awesome, thank you, Brad.
Thank you.
So that's up today. Feel free to stay until 8 p.m. Like fun. One part of the fun of meetups is hanging out and like talking with each other, like until AI also replies on that. So see you all next time.